Okay, so we will continue with the six-dimensional superconformal field theories.
Hello. Hi everyone. Hi everyone at home as well. I haven't seen anyone actually look at that camera. So yeah, thanks very much to the organizers for inviting me to speak. As you've seen, I've bowed to social pressure and put on my last jazzy shirt of the conference, especially for the talk. And so I'm going to talk to you about five-dimensional path integrals for six-dimensional SCFTs. This is based on recent work with Neil Lambert, Arthur Lipstein, and Paul Richmond. I'll give you a quick overview of really what I want to talk about. I first want to discuss a problem that will be familiar to some of you, which is the fact that there is no real convincing Lagrangian description for six-dimensional SCFTs. Then I'm going to change gears somewhat and talk about some five-dimensional gauge theories which have non-abelian gauge symmetry, and they have a large degree of supersymmetry, but they're actually non-Lorentzian. And then finally, I'm going to make a proposal. I'm going to describe how these models actually realize six-dimensional physics, and also kind of explore a few other aspects, which in particular contextualize these results more broadly. So first, this problem. My aim really here is to try and, we want to get better at computing dynamical observables in six-dimensional SCFTs. We can do a lot with symmetries these days, obviously more than ever, but still I want to be able to calculate things which aren't fixed, even by bootstrap methods. Now, although I'm not really going to talk about M theory that much, it's important to note that the AN-1 models, 2,0 models describe M5 branes. And indeed, this does open the window to using holography to study these models. And indeed, in the larger N limit, in the bulk, we have just the supergravity approximation is very, very good. And we have a lot of control. Big problem here, and kind of Fernando touched upon this at the start of the week, is that if I go to finite M, this corresponds in the bulk to M theoretic corrections to supergravity, which we don't, beyond leading order, we don't really have much control over at all. Now, the thing here is I want to just stick in the SCFT. I don't want to go in the holography. I just want to see what I can do in the SCFT itself. And the thing is, a lot of the exact techniques that have come up in recent years, like SUSY localization, really rely on having a useful Lagrangian description. And the big problem here is that we don't have this for six-dimensional SCFTs. It'll be useful later to note a situation in which we do have a Lagrangian description. This is when we wrap these M5 branes on the M theory circle. And certainly when this circle is small, we have a good description in terms of D4 branes in 2A, described by maximal super-Yang mills in 5 dimensions. And indeed, we can even realize Kaluza-Klein modes through instantons. And there are indeed proposals that these 5D Lorentzian gauge theories can be useful even to probe the UV dynamics where this M theory circle unwinds. But it's still not clear to see how, practically speaking, you can use this to compute observables in this unrolling limit. So now, like I said, I want to change gears slightly and talk about some 5D gauge theories, although now I'm going to talk about some six-dimensional coordinates. I'm going to take these coordinates x plus, x minus, and xi, where this x plus runs over a finite interval of length 2 pi. And I've got this omega ij, which is constant and anti-self dual and square -1. I'm just going to tell you that this metric is conformal to the Minkowski metric, so the same conformal class. And so to put a CFT on the Minkowski metric is to put it on this one. So let's do that. And I'm also going to reduce into modes along this interval. I can ask first the kind of most basic question: what happened to the conformal group? What subgroup of the conformal group, or what subalgebra of the conformal algebra is preserved by each level of the Fourier series? And the answer is fairly simple. There's a U1 factor, which is translations along this interval. And I have this SU13 factor, which is harder to see, but it does include this inhomogeneous scaling symmetry that Vita touched upon, and I'll have more to kind of relate it to what Vita said a bit later. I should say as well, this compactification breaks only a quarter of the supersymmetry. So now I want to propose a Lagrangian description for modes on this interval. And I'm not going to use any of, one thing to say is I'm going to focus on 2,0 just for simplicity. I am not going to use the details of this action in this talk, but if I'm giving a talk on the existence of an action, I need to state the action. There's a couple of things to point out. There is a coupling. I've written it in this way. G squared goes at 1 over K. I've written it in that way for a way that reason becomes clear. This is the field content. The real main thing to point out is there's a self-dual spatial two-form Gij, which acts as a Lagrange multiplier. And this puts you down onto what I'm calling here omega deformed anti-instanton modular space. This because this curly Fij is not quite Fij, it's omega deformed by these terms. And similarly, these derivatives are weird too. Like I said, I'm not really going to talk about dynamics there. I really want to just talk about symmetries. The first thing to say is just taking all my field content to be smooth and just thinking about this theory classically. This theory has exactly the right symmetries to describe the zero modes of this compactification. It has a SU13 spacetime symmetry. Another way to say this is it has U1 cross SU13, but nothing is charged under the U1 factor. And it had a manifest SO5R symmetry, and it also has 24 supercharges, which is a lot less trivial to see, but it does. Now, holograms in the title of this conference, so I just say where this theory comes from. It wasn't just plucked out of thin air. Point is, if you go to the bulk and you view ADS7 as a circle fibration over CP3, whack a bunch of M5 branes at fixed CP3 radius and reduce on the fiber. You get down to a 5-year Yang-Mills-like model. And then the really non-trivial step, although even to there is kind of non-trivial, but the really non-trivial step is taking those M5 branes to the band. The kind of divergences you find are actually subtly related to what Eric spoke about at the very start of the week. In particular, you find divergences in the action and also in the supersymmetry variations. But a few years ago, we kind of came up for a procedure to still propose an action at the end of this flow to the boundary. And what you end up with is that action on the previous slide. And I'll briefly say the generalization of all of this to 1,0 with more general matter content is known. I'm not going to really talk about that. So I promised you 6-dimensional physics, and so far I've only shown you 5-dimensional physics. How do I realize modes on this interval? In exactly the same way you do in Lorentzian Yang-Mills, you realize them through instantons, or rather instanton operators. These are operators which are charged under the U1 topological instanton charge, realize clues of finite momentum. This is kind of in analogy with what's done in Lorentzian Yang-Mills, but I'll go through it anyway. Point is, I'm going to pick some points in my space-time, and I'm going to extend my configuration space to not necessarily be regular at these points. I'm going to allow for a broader class of bundles characterized basically by their second Chern number measured around these little insertions. So these can be integers, and indeed solutions to this constraint equation, which have these integers non-zero, are known. Please do ask me about them. I'm not really going to talk about them too much today. And the crux of it really, again, I want to bring it back to symmetries, is that the SU13 spacetime symmetry is actually broken. This at first seems like I've gone the wrong way. I wanted to enhance it with a U1 factor, but I seem to have broken it. If you think about it from the 6-dimensional perspective, this is actually kind of what you wanted to happen. But for our purposes today, the crux of it really is that the non-invariance of the action is local to these punctures. And this is novel, and it's precisely what you need in order to recover symmetry in the quantum theory. Let's see how that works. Now I want to compute some correlators in the quantum theory. These insertion points where I've got this non-trivial instanton number measured around them are encoded in the quantum theory in a way they have been for a little while now, and this is with instanton operators. These are kind of generalizations or different, similar to monopole operators in 3-dimensional gauge theories. And the point is that I whack one of these in my path integral, and it tells me what my boundary conditions near this point is. There's a very important result here, which is that the previous slide was rubbish. I was talking about the classical theory, but it's nonsense. As soon as I allow for these configurations, the action is no longer single valued on the configuration space. We were actually able to construct closed paths on a configuration space around which the action picks up a shift. So the classical theory is nonsense, but the quantum theory is still cool as long as each of the IS is single valued. Again, this is very reminiscent of the Chern-Simon series. And the quantization we found is K as half integer. Now, like I said, classical symmetry is broken, but you can still recover symmetry in the quantum theory. And you can play the usual tricks in deriving ward identities with a few shufflings around, and you get just, I've written a ward Takahashi identity here, but it's really just of the normal form. For U1 cross SU13, but the important thing here is now I have things charged under this U1. And so I have things which have Kaluza-Klein momentum on this interval. I should briefly say the solution for scalar operators for these Ward-Takahashi identities is the general solution is known. We found it last year. And in particular, the 2-point function is totally fixed. So this is certainly a much stronger symmetry group than the Poincare group in 5 dimensions. Not quite as strong as the conformal group. The 3-point function is only fixed up to a function of one variable. But certainly, I think there is, just forgetting about the six-dimensional interpretation for a second, there's definitely a direction to go in terms of imposing this symmetry constraints on correlators more strongly. So here's kind of the punchline. The punchline is that these instanton operators carry charge under this U1 factor. Again, this is familiar from Lorentzian angles. And they carry charge k times n. Like, remember, k is discretized inverse coupling. The big takeaway here is that if k is integer, then if I take a local operator in my theory and dress it with an instanton operator, I find the k-nth Kaluza-Klein mode on this interval. And so I can interpret this theory indeed as a six-dimensional CFT on this weird orbifold of Minkowski space. And so in particular, the k equals 1 theory is just flat space, and there's no orbifold at all. So kind of the mantra here is that if I want to compute a six-dimensional observable, let's decompose it into a Fourier sum of these five-dimensional observables and seek to compute these in the theory instead. The real hope here is to offer a window into computing these observables from a five-dimensional perspective. I finally just want to bring up a couple of other aspects which will kind of tie this into other work. Firstly, if I go to k equals 1, I'm at strong coupling, and there's no orbifold, and so I should realize the full 2, 0 superalgebra. And so my symmetry should be enhanced even further. I'll show you how this should work. My SE1 3 spacelength symmetry should be buddy up with my U1 topological and give me an SO2 6 spacelength symmetry, full conformal group in 6 dimensions. My supersymmetry should be enhanced, and the R symmetry just comes along for the ride. Now, it's interesting to note that at a group theoretic level, once you forget about the signatures of these various groups, or you know the real form of the corresponding algebras, this is identical to the symmetry enhancement experienced by the ABJM theory at strong coupling. There, however, it's the topological current, symmetry which buddies up with the SE4R symmetry to give you an SOA R symmetry. The fact that these are this M2, M5 analogy works is actually really clear holographically. The point is in ABJM, George radius 4 cross S7, it's the S7 which is fibered over a CP3, whereas in this construction it was an ADS7 which was fibered over a non-compact CP3. The last thing is a relational recovery of a kind of classic description of the M5 brane as a somewhat degenerate limit of this construction. I can introduce a parameter R and rescale my fields and coordinates by it, so that now my interval is of length 2 pi R. And if I take this R to infinity, I just get back to light cone coordinates. I haven't done anything. But I don't want to do that. I want to take my orbifold parameter large and my R large, but their ratio fixed. All I get down to is now Minkowski space with a compact null direction. And some of you may recognize this as precisely the geometric setup of discrete light cone quantization, or DLCQ. And my action simplifies a lot. Basically, anywhere I saw an omega ij gets scaled away. And my action simplifies a lot. And in particular, now this Gij just imposes the anti-instanton equation. And a few years ago, I worked out how to actually do this explicitly for this model and work out what is basically a supersymmetry preserving deformation of superconformal quantum mechanics on instanton moduli space. This is kind of the content of the original DLCQ proposal for the M5 brane. There is, we don't understand it fully, but there seems to be some sense in which ambiguities associated with the DLCQ proposal, such as the so-called zero mode problem, seem to be in some way regulated by approaching the DLCQ limit from large but finite K and R. Like I say, I don't have anything conclusive to say on that, but I definitely think there is something to be said. Let me finally conclude. Hopefully I've convinced you that these five-dimensional models may be helpful or useful in encoding six-dimensional CFT dynamics. The kind of zeroth order next step is to really understand how this symmetry enhancement and strong coupling works. In particular, like I said, at k equals 1, symmetry should be enhanced. What I'm interested to see at this point, and what I'm kind of expecting to see, is a restriction to ADE gauge group at this point. We know that 2, 0 theory should really only be around for ADE gauge group. And so I'm expecting that there to be some obstruction for non-simply race groups here. Now, if I can show, or if someone can show this strong coupling enhancement, we can confidently compute six-dimensional SCFT observables in this theory. Now, how do you actually do that? The main thing to have in mind is that there's a very large degree of supersymmetry. And so it seems like a prime target for SUSY localization. Kind of a first thing you might want to try and do using this is to get a new formula for the superconformal index in 6 dimensions. This is something which has already been tackled by Kim Young Lee and collaborators also using kind of deformed five-dimensional gauge theories. It'll be interesting to get a new formula which may be useful in different regimes. Ultimately, the big goal is complete correlators at different regimes of this orbifold parameter k. At large k, we're at weak coupling, and perturbative techniques will work or should work. It's a strong coupling that I think localization may come to the rescue, and it'd be very interesting to try and compute explicit things at strong coupling. And finally, the large n limit of this theory should be some kind of simplifying limit. As I said at the very beginning, this will just match with the supergravity approximation. There's certainly some kind of planar limit or some kind of at least some kind of simplifying limit should emerge at large n, but it's not something we understand yet. The very last thing to note is that the symmetry algebra of this theory is just a different real form of the superconformal algebra of the ABGM theory, which in particular admits a Yangian extension. I know that Niklas and co in recent years have even found that at the level of the ABGM Lagrangian. So it'd be very interesting to see if the same structure emerges, and therefore if integrability techniques are useful in this theory to compute things. That's me. Thanks very much.
Thank you. Perfect timing.
Actually, maybe it will help if we could show the slide of the action. So, from the 5D point of view, this is probably like non-renormalizable. So, you mentioned that as a function that's the 60.
Yeah.
And do you think that do you think that in principle could allow you to compute things of the 60 period that are not BPS? In other words, maybe for BPS things, the relevant operators that you have to complete BPS trivial and so on. But do you think in principle you could use this to compute non-BPS? Or could it be that you need additional degrees of freedom?
It's a very good question, and my kind of interpretation of it, or my answer is kind of informed by this DLCQ limit, where the dynamics truly does go down to just moduli space quantum mechanics, which is in many ways, an easier thing to handle. This constraint, this anti-instanton or omega deformed anti-instanton constraint, I think is obviously constrains the dynamics. And without understanding that better, I don't think I can really answer the question. Certainly it is the case that things like superconformal indices in really maximally refined superconformal indices in 6 dimensions have been computed using 5-dimensional, clearly perturbatively non-renormalizable gauge theories, and so certainly those kind of things would be fine. But obviously your question is about non-BPS things, and the answer is I don't understand this theory well enough to know.
I mean, maybe you comment a little on what do you think is better about this dimension 5D compared to
in my mind, it's because strong coupling is achieved at k=1, whereas in 5D maximal super Yang-Mills, to go to the UV, you genuinely need to go to infinitely large coupling. There's no.
Maybe to make sure I understand, I mean, suppose I take this branches that we have to pick finite or large carriage. Isn't it still because it isn't?
It doesn't. So it only has the kinetic term. So it's a weird thing.
So you have to scale that away.
There's no G Yang-Mills in here.
I guess I was confused. How is trace of F squared dimensionally?
Yeah. So here, this has to do with this parameter R. Really here, everything is dimension is defined by its Lifshitz dimension under this inhomogeneous scaling. So the x minus direction carries weight 2. whereas the xi direction is weight 1. In terms of studying the dynamics of this theory, it was useful that Vito came before me because a omega deformation of this Nishida sun map, where you map to particles in harmonic potential, extends here. So in this DRCQ limit, you do truly get the Schrodinger algebra, and then everything that Vito said completely applies. Even before you scale away this omega ij, you still have this Nishida sun map. And so I do think there is hope, and it seems to be going in the right direction to be able to relate the dynamics of this theory to particles in some kind of harmonic potential, which would obviously be tractable.
That's interesting. Very sure.
Just a basic question. So you put the theory on a finite size interval x plus. What boundary conditions you put at the end, and does it matter?
It's a very good question. Ultimately, the minimal boundary conditions that allow you to do a Fourier expansion. And so you need things to die away sufficiently fast. It's not really that fast, but you still do need boundary conditions. Asking what happens when those boundary conditions are violated is kind of an important next step, I think. But for the sake of this work, so long as your boundary conditions on operators or rather their expectation values is enough for a Fourier expansion to converge, then you're fine. Generalizing that to more general boundary conditions or boundary behavior is an open thing.
Okay, so in view of time, let's thank Rishi again for his talk.